experiment A1, the aim of the titration is to calculate accurately the concentration of this hydrochloric acid solution. So the solution is of the order of 0.075 moles per decimeter cubed, but we don't know how the actual accurate value is, so that's the aim. To start off with then, the hydrochloric acid will go in this piece of apparatus which is called a burette. Now the burette is an accurate and precise measuring device for volumes of solutions or liquids, solutions in this case. It's got a scale up here, and notice that it runs from 0 at the top down to 50 at the bottom. So the scale is a little bit interesting. It goes 0 at the top to 50 down at the bottom. The first thing to do then is to check that the burette is set up properly and to rinse it with the solution that it will eventually house. Notice I'm not rinsing this with distilled water, because if I did that, distilled water would remain in here and that would dilute down the solution that I'm interested in. So I'm going to take some of that hydrochloric acid. Holding this burette funnel at the top, a plastic funnel at the top, I'm just going to lift it up so that there's not an airlock around that funnel. So just holding it just slightly higher than there with my finger. And then I'm going to pour into here, I don't know, about that much. It doesn't really matter how much, just a small quantity of solution in there. Just take the funnel out, and these are really dilute solutions, so it's okay to just sit that down on the bench. Notice the tap is horizontal here. So the tap has a stopper with a hole running straight through it. It goes the same way as those little things. So it's horizontal at the moment, which means it's closed. If I make that vertical, that opens the tap. I'm just going to check around me that I don't knock anybody with this. I'm just going to just very carefully twist and pour that solution so that it covers all of the inside surface of the burette like so. And then I'm going to hold it over the sink and open the tap to allow that solution to just drain through, just like that. So that makes sure that all of the surface of that burette has been rinsed with the appropriate solution. Now it takes ages for that to go through, so now that I've rinsed that tap, I'm just going to close the tap, look behind me, turn it upside down, open that to let the rest of that solution out, and that drains out much quicker now. Okay, second job then is to fill the burette, again with the HCl solution. Notice how I've labelled the beaker, because quite often titrations deal with lots of colourless solutions, so it's easy to get mixed up. It's a good idea to label stuff so that you don't get the wrong solution in the wrong place. So pouring in the solution, it does not have to reach 0. So I'm just going to top it up. I've actually emptied the beaker, so I'll need some more solution in a moment. And this time I'll pop that funnel in there. Make sure the funnel is out of the burette as soon as you do anything else, because if the funnel sits at the top of the burette, the funnel itself might have drops of solution on it, which then might fall down into the burette during the titration, thus causing the results to become inaccurate. Again, remember, I need to go over the sink and just make sure that this is full of solution, so the jet's full. Just doing a quick visual check that there's no air bubbles, and then I can use this clamp and stand to clamp that burette like so, nice and vertically. Now, important safety things when using the burette. Notice how I lifted this down below eye level to fill it, because if I fill from up here and I spill solution, it could go down the back of my safety glasses, so that's no good. So I need to lift it down. Some people might be tall enough to just pour it in, that's fine, but it's better to just lift that down and to check. The second thing that I would need to do is just lower the level of the burette in order to read the starting reading, but we'll go into the readings on that scale in a few minutes' time. So the first piece of apparatus, in this example housing the dilute hydrochloric acid solution, is this burette. The second piece of measurement apparatus for volumes of solution that we're going to use in this titration is this. It's called a pipette, or a graduated pipette, or a volumetric pipette. All of those words are fine. In this pipette there's a line here, and this graduation mark is used to measure out a set volume. In this case, for this size pipette, 25.0 centimetres cubed of solution. Just like with the burette, I need to rinse this with the solution it's going to deliver, and in this example it's sodium hydroxide. Safety fillers are always used on pipettes. Believe it or not, back in the day they used to pipette and use this like a straw and draw the solution up, but that's obviously not allowed now and is a poor idea. So instead we use a safety filler. But it's important to attach the safety filler onto the pipette as follows. Firstly, support the pipette right at the end where the safety filler is going. Otherwise, if you have your hand further down, essentially what's happening is the glass is trying to be bent, it will smash and it could end up into your hand, and that's a nasty and actually quite a common glassware injury. So hand nice and close to the safety filler. And then the safety filler goes on firmly, but you don't need to absolutely ram it on, it just needs to be on firm enough to create a seal. The next thing I'm going to do is rinse the pipette. So I'm going to put the bottom of this pipette into the solution and draw up the solution until it's something about half full, then lift it out of that beaker like so. Then I'm going to very carefully turn it onto its side, pretty much horizontally, and move towards the sink, and just push it up with my thumb and remove that safety filler. Now what I'm being careful about is to avoid the solution getting to the end, because I don't want the solution to contact with the safety filler on the next go, because that contaminates the experiment and also means that the filler doesn't work properly. So I'm going to just release the pressure on my thumb slightly, let the solution about halfway up, twist it round like so, and this time hold it straight over the sink and just let that drain out. And it's a patience game, this one. I'm just allowing that solution to drain under gravity like so. Now on this occasion, because I'm rinsing this, and on this occasion only, I'm just going to give that a little shake to get rid of the rest of the drops in that pipette. I'll then take the filler, again, hand nice and close to the end, pop the filler back on, and this time, filler goes into the solution, and I'm going to take the solution until it's about halfway between that graduation mark and the filler itself. So I'm still bringing solution into this pipette like so. Nice and slowly when it narrows, because it goes a lot faster upwards when it narrows, and stop about there. Next thing I'm going to do then is swap my thumb for the filler. So a good way to do this is push upwards with thumb and make sure that the really fleshy part of your thumb sits on top, just like this. 1, 2, 3, up and over like that. Now, it's important to make sure the bottom of the pipette is not sitting in the solution for the next part, because if it does, that will push everything back upwards and actually will give you an inaccurate result. So take the end of the pipette out of the solution, like so. You can just hold it with your finger and thumb down here to hold it steady. Then with your eyes on the line, so that your eyes are at the right level, so your eyes at the same level as the graduation line, just letting the pressure off your thumb altogether. So you're not moving your thumb altogether, it's just letting the pressure go so that that solution is going nice and slowly into the beaker. You can practice this with a drinking straw. Try and just drop one drop at a time, and that's the method that you need to use. Nice and slowly, let the bottom of the curve, that's the meniscus, just sit on the line, and then transfer it to a conical flask like so. Just allow it to drain under gravity. Nice and patiently, allow that to drain down. And this time, the final step is to just touch the surface of that solution with the end of the pipette. You'll notice that there's a little drop of solution still inside the pipette. It's calibrated to deal with that, so that's the accurate delivery under gravity of that volume of solution. So key points for the pipette: rinse the pipette with the solution it's going to be used to deliver, so this time sodium hydroxide. Then use the solution, use the pipette filler to overfill slightly. Allow the bottom of the meniscus, that's a little curve that's formed by the solution, to just sit on that graduation mark. Then transfer to the conical flask, allow it to drain under gravity, and finally just touch the surface of the solution with the pipette. And that's now exactly 25.0 centimetres cubed of sodium hydroxide in this flask. So in the conical flask here, I've got the 25.0 centimetres cubed of sodium hydroxide solution that I delivered using this graduated pipette. I talked earlier about the meniscus, and the meniscus is the little curve that aqueous solutions form. It's a consequence of the surface tension of water being quite high, and so the bottom of the meniscus sitting sitting on the graduation mark is commonplace to lots of graduated glassware. So the pipette looks like this when it's been used properly, and the burette reading of 3.35 centimetres cubed looks like this. I'll come back to that in a moment, but the pipette is always used to deliver a fixed volume, a portion, if you like, of that solution. And the technical term that we use for that is aliquot. So if you see that term, all it means is a portion of. Now I'm holding this in my hand still. I'd like to put this down safely so that it doesn't roll and smash off the table. So I'm just going to pop it down next to the gas tap and put the filler like that, and that will be perfectly fine now. Back to the burette. So the burette scale between the 0.00, so between 3 centimetres cubed and 4.00 centimetres cubed, are 10 divisions. So each one of those divisions is worth 0.10 centimetres cubed. Whenever we use the burette, we use the convention that we can read the bottom of the meniscus is either sitting on one of those graduation lines or is between two graduation lines, as in this case. So in this case, a 3.35 centimetres cubed is the value I give that. So burettes are always read to 2 decimal places, where the second decimal place is a 0 if it's sitting on the line, or is a 5 if it's between the lines. And therefore we say that this true value is 3.35 plus and minus 0.05 centimetres cubed for that start reading. When I delivered the sodium hydroxide to the flask, there's quite likely to be some little splashes on the side of the flask, so I can take some distilled water and just rinse those splashes down. Now that might seem a little bit counterintuitive because we've just gone to great lengths to measure carefully the volume and measure carefully the volume here. However, as soon as any moles of sodium hydroxide enter this flask, and as soon as any moles of hydrochloric acid enter this flask, if they contact with the distilled water, that distilled water will dilute them by exactly the same quantity, and therefore that's a completely valid thing to do. And it's important to rinse the splashes down so that those reagents, those moles of reactants, can react together in the bulk solution. The next thing I need to do then is have a go at a rough titre. Now to do that, the aim really is to measure what volume of hydrochloric acid is needed to just neutralise that volume of sodium hydroxide. So I need some way of knowing whether that's happened or not, so I'm going to add an indicator, this time phenolphthalein. I'm going to add 1, 2, 3 and 4 drops this time so that I can see a nice clear pink solution in there. Using the white tile is sometimes a good idea because it's easier to see the colour in that case, especially against the dark benches, but not essential, it's just quite useful. I find it much easier to swirl with my right hand because I'm right-handed, and therefore control this tap with my left hand. And in this first rough titre, it's exactly that. I'm going to add a load of this solution until that just changes colour, turn the tap off and record the final value. Here we go. So I'm adding that solution and swirling the flask right so. Keep swirling, and it's just changed. So the final reading on this burette here then is 36.15 centimetres cubed. 36.15 centimetres cubed. Okay, so I've now got the rough titre, and that cannot be used in any calculations because it was exactly that, it was a rough titre. So to do this and use the results, what I need to do is reset the experiment. So I take the flask, empty it into the sink, rinse it a couple of times with tap water, and then rinse it once with distilled water, like so. I would then need to top up the burette, remembering to take it down below eye level to do that. So I'll top that up in a moment and add a second portion of sodium hydroxide into this flask. So add a new aliquot of the sodium hydroxide into this conical flask. So this time I've reset for the second run of the titration, which is the first accurate run, and so we could use this data in any calculations, assuming that it achieves concordancy. More on that in a little while. Set this up in exactly the same way, and the start reading this time is 2.20 centimetres cubed. Now last time, I think I've calculated that we added 32.80 centimetres cubed of the sodium hydroxide to the flask, of the hydrochloric acid to the flask, which therefore means that we're expecting this to turn somewhere around about 32.80, probably a little bit less than that, so about 31 centimetres cubed, something like that added. So what I'll do this time is I will add rapidly the solution from the burette, and then I will add that, so I'll add that rapidly to the flask, and then I'll stop adding first of all, but I'll add just less than the expected value. So if I just start nice and rapidly adding that solution from there into this flask like so, I'll keep going, until I've added just less than I'm really expecting to have to add. So I'll stop there. Now, again, this time, solution's probably splashed up the surface. So the next thing I'll do is take some distilled water and again, just rinse all the moles of those reactants into the main bulk of that solution, just like so. Now, because I think I'm quite close to the end point of this titration, that end point is the point when the indicator just changes colour. I'm going to start adding a single drop at a time, so one drop at a time of this solution, drop by drop. Still looks pink to me, still looking pink, and it has now just changed to colourless. So that's now an accurate end point of that titration. And my final value on here is 33.65 centimetres cubed. 33.65 centimetres cubed. So the final stage of this titration then is to repeat that again. If the next value is concordant, so when I say the value, the titer, the volume added, is concordant with the value that I've just calculated, concordancy is within 0.10 centimetres cubed of the last value. As soon as I get two values within 0.10 centimetres cubed of each other for the titer, then I can stop and use the data. Whenever we take a measurement in the lab, it's subject to uncertainty, and you need to be able to propagate those uncertainties in different techniques to work out overall uncertainties and measurements at A level. So in this example, we used the pipette here, and the pipette uncertainty is plus and minus 0.05 centimetres cubed here. On the burette, each reading is plus and minus 0.05 centimetres cubed also. But for the titer, that's the volume delivered, the titer is plus and minus 0.15 centimetres cubed. Now that sometimes causes confusion. Where on earth do we get this plus and minus 0.15 from? But if we imagine how this experiment was done, a starting reading plus and minus 0.05. The final reading, another plus and minus 0.05. But when we stopped this reading was within one drop of that endpoint. So that final drop, we don't know whether it was the start of that drop or the end of that drop that actually caused that colour to change. And the drop volume itself is estimated at 0.05 centimetres cubed. So add those three lots of 0.05 centimetres cubed together, and that's where we get the plus and minus 0.15 centimetres cubed uncertainty in the titer volume.